Hello friends, welcome back to our favorite channel. In the last video, we had discussed about estimation of error in the temperature measurement in a thermometer vial, and that was the last topic related to steady state one-dimensional heat transfer by means of conduction. The links are given in the description box regarding the conduction heat transfer under steady state. So friend, in the present video, we are going to discuss about transient or unsteady state heat transfer. This is a continuation of conduction heat transfer, but we are going to discuss about transient or unsteady state heat transfer. So in this video, we are going to discuss about unsteady state heat transfer, different examples related to transient heat transfer, lump parameter approach for analysis of unsteady state heat transfer. So friend, a solid body is said to be in steady state if its temperature does not vary with variation in the time. That is what we had discussed till the last video lecture. So in that case, we can say that the temperature is a function of x, y and z coordinates. It is not depend upon the time. But if there is an abrupt change in the environment or the surface temperature with variation in the time, then it is called unsteady state heat transfer. Means in case of unsteady state heat transfer, temperature is not only a function of coordinates x, y, z, but it is also a function of time, tau. So friend, we can say that under transient heat transfer or under unsteady state heat transfer, temperature distribution and heat flow at any point of the system varies continuously with variation in the time. So now we have to discuss some examples related to real life as well as related to industry related to unsteady state heat transfer. So, some known example to us includes heating and cooling of metallic billets, heat treatment of metal by quenching, cooling of IC engine cylinder, brick burning, starting and stopping of different heat exchange devices, vulcanization of rubber, cooling and freezing of food, and you can say heating of boiler tubes, rocket nozzle, etc. These all are, you can say, examples related to unsteady state heat transfer, and lot many more are there. So now if you want to solve the problems related to unsteady state heat transfer, the possible approach which are available with us includes approximation, analytical method, product solution, graphical method, use of transient temperature chart, that is Hausler charts, and numerical techniques. Out of this, we are going to discuss about approximate solution to solve unsteady state heat transfer problem. So friend, one more important thing which we can see is during the unsteady state, the change in the temperature may follow periodic or non-periodic variation. So again we have to discuss some examples related to periodic variation and non-periodic variation. So if we talk about periodic variation, in that case, the periodic transient steady state, the temperature within the system undergoes the periodic changes, which are either irregular or you can say regular, but definitely cyclic. The notable examples includes temperature variation of building wall during 24 hours, or you can say temperature variation of entire building during 24 hours, temperature variation in the surface of earth during 24 hours, temperature variation in cylinder of an IC engine, and you can say temperature variation in heat processing of regenerator. These are some notable examples related to unsteady state heat transfer with periodic variation. But there are also some examples in which temperature changes as non-similar function of time. This variation is neither according to any definite pattern or that is not repeated in cycle. The examples include heating of ingot in the furnace, or you can say cooling of metallic billets, bar and blanks for the hardening purpose. So these are two different type of variation that will be observed under transient heat transfer. So friend, whether it is a periodic variation or non-periodic variation, we have to find out what is the amount of heat transfer through the system. So the approach which we have to discuss is related to approximate solution, and we are going to discuss about lump parameter analysis, which is also known as heat conduction in the solid having infinite thermal conductivity, that is K tends to infinite, and negligible internal resistance. So this is a very important approach which may be asked in your competitive examination, that include UPSC, GPSC, IES, as well as in your regular internal as well as your end semester examination. So let us begin with lump parameter analysis. First we will discuss what is lump, and then we will discuss what is called lump parameter analysis. So friend, in the previous lectures we learned that all the solids have finite value of thermal conductivity, and because of that each solid is offering some resistance to the heat transfer. So always we observe temperature gradient within the solid, whether heat is dissipated or when the heat is added to that solid. But if we'll consider some case of a solid which is very smaller in size, and you can say that particularly if a solid body which is smaller in size having a very large value of thermal conductivity and having a very small value of surface area to volume ratio like plates, bars and thin metallic wires, in that case the temperature variation or temperature gradient within the solid is negligible, because first part thermal conductivity is high, second part the surface area to volume ratio is less. So in this case the internal resistance offered in case of Cartesian coordinate system, that is L divided by AK, where L is the length, ACS that is the cross section area, and K is the thermal conductivity of material. So L divided by AK, that is internal resistance offered, is negligible or it is very small, and hence the rate of heat transfer is totally governed by external resistance, or you can say that is a convective resistance, and its value is 1 upon HAS, where H is the convection heat transfer coefficient and AS that is surface area. So friend, above process is known as Newtonian cooling or heating, in which heat flow to or from the solid is totally controlled primarily by convection resistance, and such analysis is called lump parameter analysis, that is approximate method, because in this case the whole solid whose heat transfer at any time is a function of temperature and total heat capacity is treated as one lump. So one lump means the entire body is at same temperature. So now I hope what we had discussed is very much clear to you. We are talking about a solid body having a very large value of thermal conductivity and the surface area is very large compared to the volume, means we are talking about the case which include plate, bar and thin metallic wires. So let's start the analysis. So friend, you can refer the figure where you can see the figure number 26A, that is the general system for unsteady state heat conduction. where you will observe a very small body with negligible internal thermal resistance, means thermal conductivity is high, plus the surface possesses a large surface area compared to the volume. You can see control surface is observed, and in this system what you will observe here is Ti, that is initial temperature of the body, Ta, that is the surrounding temperature, and definitely Ti is much higher than Ta, that is internal temperature is higher than surrounding temperature. And here you can see energy which is leaving the system, that is heat liberation, that is equals to heat transfer by means of convection only, because it is the totally controlled by the external resistance, that is convection heat transfer. And here also it is given that tau equals to 0, means when the time is 0, temperature equals to initial temperature, and when time starts or when the time is greater than 0, the temperature is the function of time. So here under unsteady state heat transfer, the temperature of the body is a function of coordinates plus it is a function of time. So that is shown in figure number 26a. The figure number 26b, that is talking about equivalent thermal circuit. And here in the figure number 26a, you can observe some equation, that is E out, that is equals to Q convection, and that is equals to HA delta T, and that is equals to minus rho Vc into dt by d tau. Whereas the equivalent thermal circuit is indicating CTH, that is capacitance, thermal capacitance, that value is equals to rho CV, S, that is a switch that will either complete the circuit or incomplete the circuit, RTS, that is the thermal resistance offered, and that value is 1 upon H into AS, that is the convection resistance offered. Two temperatures you can see, Ti and Ta, that is the initial temperature and ambient temperature. So friend, I hope the figure number 26a and figure number 26b is clear to you. And now we will start to discuss about lump capacity analysis for the system. So according to the figure number 26, we can consider a small body with initial temperature of Ti, and suddenly that body is placed in the bath of liquid, or you can say that is kept open to the surrounding where the constant temperature Ta is observed. So the heat start to dissipate into the surrounding or into the liquid by means of convection, and convection heat transfer coefficient is predominant in this case. In absence of any temperature gradient in the solid, the energy balance is equals to, you can say, the rate of heat flow out from the solid through the boundary, that is equals to the rate of decrease of internal energy of the solid. So you can say Q, that is equals to minus rho Vc dt by d tau, and that is equals to H into As into T minus Ta, where we can say that M, that is density into volume, that is called mass of the body in kg. Rho, that is the density of solid in kg per meter cube. V, that is the volume of the body in terms of meter cube. C, that is the specific heat of the solid body in terms of joule per kilogram degree Celsius. dt by d tau, that is the temperature variation in time, unit is degree Celsius per second. T, that is temperature of body at any time, unit is degree Celsius. H, that is the convection heat transfer coefficient, unit is watt per meter square degree Celsius. And AS, that is the surface area of the solid body in terms of meter square. So I hope friend the equation 1 is very much clear to you. The nomenclatures are also discussed. Plus you can see Ta, that is the temperature of surrounding air or the temperature of liquid bath in degree Celsius, and tau, that is the time. So when the initial temperature of the solid is Ti and when time is 0, that is our first boundary condition. But as soon as the time is greater than 0, means we are putting the object in a liquid bath or in atmospheric air. So you can say that H into As into T minus Ta, that is energy dissipation from the solid to surrounding, that is equals to minus rho Vc into dt by d tau. Here negative sign indicate there is reduction in internal energy. Now we know that theta, that is equals to T minus Ta, that is temperature axis. If I will write theta into tau, then I can say that is equals to T tau minus Ta. And if I will go for differentiation of it, that is d theta by d tau, I will get that is equals to dt by d tau. So now in the equation number 1, I can replace d theta by d tau as dt by d theta. So if we'll rearrange that equation, we can say that d theta by theta, that is equals to minus HA divided by rho Vc into d tau. So now if we'll integrate this equation on both the side, we'll get integration of d theta by theta, that is equals to integration of minus HAS divided by rho Vc into d tau. And upon integration we will get ln theta, that is log base E into theta, that is temperature axis, that is T minus Ta, and that is ln theta, that is equals to HA divided by rho Vc into tau with negative sign plus C1, where C1 is the integration constant. So now to find out integration constant, we have to apply boundary conditions like what we did in case of steady state heat transfer in the Cartesian coordinate system, in the cylindrical coordinate system, as well as in the spherical coordinate system. So now we will apply the boundary condition and we try to find out solution of equation A. And we know the boundary condition, that is when tau is 0, when time is 0, the temperature is equals to initial temperature. That is when tau equals to 0, T equals to Ti. And when we'll put these values in equation number A, we will get C1 value, that is ln. Ln means log base E, that is ln. So C1, that is equals to ln into Ti minus Ta. So Ti minus Ta can be written as ln into theta I. So hence this ln theta, that is equals to minus Ha divided by rho Vc into tau plus ln theta I, that is equation 1 is shown with value of C1, that is ln theta I. And now when we will go for simplification of this equation, I can write theta upon theta I, that is equals to T minus Ta divided by Ti minus Ta, that is equals to e raised to minus Ha divided by rho Vc into tau. So this equation B is a equation which indicate the temperature variation into the body, that is into the solid body, when it undergoes unsteady state heat transfer, where T, that is temperature at time tau, Ta, that is the surrounding temperature or liquid bath temperature, Ti, that is the initial temperature of the body, H is the convection heat transfer coefficient, As, that is the surface area of the solid body, rho, that is density of solid, V, that is the volume of solid, C is the specific heat of the solid body, and tau is the time. So equation B indicate the temperature variation under unsteady state heat transfer for the body. So friend, I hope it is very much clear to you how to derive this equation. So the equation B, what we have discussed is plot in the graph of figure number 27 for the different value of Ha divided by rho Vc. and the observation which we can see that includes the time required for the solid to reach some temperature is T. So if we want to know what is the time for one particular temperature, we can get, or if some temperature is known to us, or if we want to achieve this temperature, what is the required time, that is calculated with help of equation number B. The second observation which we can see is the temperature variation in the body is approached to the bath or surrounding air temperature TA exponentially. The temperature of the body changes rapidly at the beginning due to the large temperature difference, but the temperature change is slow down at later stage. The large value of HA divided by rho Vc indicate that the body will approach the ambient temperature in the very small time duration. And the third observation which we can see is the quantity rho Vc divided by Ah has a dimension of the time, and it is called thermal time constant, and that is denoted by tau Th. So the tau Ts, that is rho Vc divided by h into As, and its value is indicative of the rate of response of a system to the sudden change in its environmental temperature. Means if a hot metallic billet is suddenly quenched into the water or a brine solution, there is a drastic change in the temperature, and that variation in the temperature is observed by thermal time constant. So as we have discussed, the RTH, that is 1 upon HA, that is the thermal resistance offered due to the convection heat transfer, and CTS, that is rho Vc, that is the thermal capacitance or stored energy in the equation C, that is equation of time constant, that is rho Vc divided by H into As, where we can write rho Vc, that is Cth, and 1 upon Ha, that is Rth. So tau Ts, that is the thermal time constant, that is equals to Rth into Cth, where Rth, that is thermal resistance offered, and Cth, that is the thermal capacitance observed. So friend, this is about the theory related to lump capacity analysis, that is the analytical approach to find out temperature variation under unsteady state heat transfer. So friend, in this video we had discussed about what is called unsteady state heat transfer, what are the different examples related to unsteady state heat transfer in real life as well as in actual application. Also we had discussed what are the different possible methods to solve the numerical related to unsteady state heat transfer. Then we had discussed about periodic and non-periodic variation under unsteady state heat transfer. We had discussed about what is called lump. We had discussed about lump parameter approach. We had discussed about thermal time constant and what is significance of thermal time constant in the real situation. So in the next video we are going to discuss about dimensional analysis for the different quantities related to transient heat transfer and numerical based on that. So if you like this video, then do not forget to subscribe this channel as well as do not forget to share this channel. Have a nice day. Thank you. Goodbye.